So let's get it started by considering two graphs. So we'll start with just the functional part here. So from what we've done previously in here and pre-calc and other algebra in the past, if I looked at the graph on the left and I said, what is f of 2? When x is 2, I have no solution. What about over here if I said, what is f of 2? It's 2, right? Okay. So what about the limit? What about the limit of f of x as x approaches 2? Does the limit exist? When you think about the limit, one of the things to think about is our definition of a limit. For every, right, epsilon greater than 0, there's delta greater than 0, right? That absolute value, x minus c is less than delta, right? But what's not said there is it also has to be bigger than 0. What that means is x never equals c. F of x never equals L. If I go back to when we first started this with our train example, which was way back here, if I kept getting closer to 2, if you remember our formula, here was our formula, right? Then we put our thing in. Could I put 2 into there? No. So I could not put 2 in. So I could not put c in. It makes it undefined. So from looking here, looking over here to the right, I could never put 2 in. So is this ever going to truly equal 16? No. So how close could you get to 16? Pretty darn close. As close as you want. As close as you want to get to 16, that's epsilon. There's a delta. There's just a delta. That if you're close enough to 2, it will get you that close, right? That's the whole definition of a limit. So instead of saying close to and that, it's like, okay, how close do you want to get to 16? I can find an x that will get you that close. That's the idea of what our definition of a limit is. But we never actually put 2 in, and we never actually get to 16. So if we go back to that graph, make this closer together. And you think of here, as you get close to 2, if somebody's walking on this graph, what do they get close to? But what value do they get close to? 2. The y. What do they get close to the y value? 1. So as they get close to 2 on the x-axis, they get close to 1 here. And it doesn't matter if they are moving this way or they're moving this way, they get close to 1. What about over here? As I walk on this graph, what do I get close to as x approaches 2? 2. I get close to 1. So in both of these, the limit as x approaches 2 is 1. Even though here there is no functional value at 2, and here the functional value at 2 is 2. Okay? Let's look at some more. So I'm going to let you write down these answers before we say them out loud, so don't spoil it for anybody. So looking at this graph, what is the limit of f of x as x approaches 3? So write down the answer. As x approaches 3, what's the limit? And the answer is 2. For the next one, what is the limit as x approaches 2 of f of x in our graph? The answer there is 1. And finally, what is the limit as x approaches 1 of f of x in our graph? And the answer is D and E.
Of course it's different.
Does not exist. No solution would work. That would also work.
Why is it D and E?
So think about this from our guy walking on the graph. If I am walking this way, what was that? Yep, not opening. There we go. Group this guy up here. So as this guy walks this way, what is he getting close to?
One.
He's getting close to 1. But he's over here as he's walking, what's happening? He's getting close to 0.
It can't be negative.
What do you mean he can't be negative?
Like, never mind.
So from over here, he's getting close to 0. Over here, he's getting close to 1. So we have different limits, right? No. What that's actually going to lead us to is one-sided limits. A right hand or a left-handed limit. Yes. Well, they're not called that, but I like that definition. We'll talk about that in a second. So, right-handed limit is the limit as x approaches c plus is the limit from the right. Okay? Now, this means as f of x gets close to L, x gets close to c from the right. So the important thing here is it's got the little plus. So I'm going to go back to the last picture here for a second. So if I am approaching c from the right, that means this guy is moving this way from the right. I'm coming from the right. Don't get confused as I approach from the right, which way am I moving? Left. But I'm coming from the right. We also can have a left-hand limit where it's c to the minus. That is a left-hand limit. So, let's look at this with our left and right hand. So I'll let you finish writing before I go on here. And we're going to compare these with what we did on the last ones up in the top right of your notes here. The limit of f of x as x approaches 3 plus. Plus means from the right. So as we approach 3 from the right, our limit is 2. That's the same thing we had at 3. So what is our limit of f of x at 1 from the left? So as you approach 1 from the left, it goes to 0. What's that? Why? The epsilon and delta are 0 is just like what your answer is. It's your L, right? It's not the thing that has to be 0 is the distance between f of x and L. And the idea here is, and understand, the idea here is this is 0. Is it ever equal to 0? No. In the limit, it's 0 because we're getting closer and closer to 0, but we never actually get there. But how close can you get to 0? As close as you want, because there's an epsilon. How close you want to get, we can find a delta that gets you that close. And I'm going to keep saying that over and over again just to keep driving that idea home. that it never actually equals 0, but in the limit, it gets as close as you want to 0. There's an x that can get you that close, even though it never actually is equal to 0. So what is the limit of f of x as x approaches 1 from the right? From the right, it is 1. So you notice we can have the limit from the left and the right be different. Now consider 3. The limit from the right is 2. What's the limit from the left at 3? It's the same. So we have, that can happen. Finally, what is the limit at 4 from the left? What's the limit of 4 from the right? Does not exist, right? Because no solution. Because there is no right. Yeah.
So, the 1 minus has a limit of 0, and the 1 plus has a limit of 1. Why did just the 1 have the DME at the top?
Because of theorem Bob. That's my name for it. So I like to give names to theorems so that when we, in our book, this is just called theorem 3. So that's boring when in a month when I say, well, you remember theorem 3, you're going to be like, no, I have no idea what that means. But you'll remember theorem Bob. I gave it a name. Okay. Now the name also has meaning. Why I picked Bob and not like Steve or something else. Bob has a reason. I'll explain in a second. Here's what this theorem says. The limit as x approaches a number is equal to L. I'm going to stop and let you finish writing because you're all writing, which means you're not listening to a word I'm saying. So I'll let you write it down and then I'll talk through it. All right, so here's what it says. The limit of f of x as x approaches c equals L. That means the limit exists at a number. IFF is if and only. Do you remember what if and only if means from geometry? Yeah. It goes both ways, right? So if it is a dog, it has 4 legs. If it is 4 legs, it is a dog. That's not if and only if, right? Doesn't go both ways. So, but this says if the limit exists at a number, if and only if the limit from the left is equal to the limit from the right. So what that means is if we go back to our picture, the limit at 3 existed because what's the limit from the right and the left? The same, 2, so the limit at 3 exists. At 1, the limit from the left and the limit from the right are not the same. Therefore, the limit at 1 does not exist. That's kind of your question, right? That was what you were asking. So, why do I call it theorem Bob? Because this whole thing is the limit from the left and the right have to be the same. And when Bob, the left and the right is the same. So that's why I call it Bob. What's that? Palindrome? Close. There's the P. Right? So, it's calling theorem Bob because the idea here is for a limit to exist, the limit from the left and the right have to be the same. And if you know the limit from the left and the right are the same, if and only if means the limits that is that, or if you know the limit exists and you know the left and the right are the same. It's the same from the left and the right. Hence Bob. It's the same from the left and the right. That's kind of how, where that comes from. Okay. All right. Let me. I'm gonna go back. Singing back there. Hopefully all this is coming through on the microphone as I'm recording right now. So about some limits involving infinity. Now, there's one type of limit to infinity, and that's this. This is the sine of x over x as x goes to infinity. So that's the one type of limit where this goes to infinity. We'll talk about this later when the limit actually goes to infinity. What we want to talk about here is when your answer is infinity. So we want to look at the difference, not that. So let's look at this. Find the infinite as x approaches a. So I want to find right here. What is the limit of 1 over x minus 2 as x approaches 2 from the right? Now, does the limit at 2 exist? Can you plug 2 in? No. Does that mean, though, that it doesn't exist?
No.
Not necessarily. So we're going to have to look at it from the left and the right. And if the limit exists at 2, what has to be true about the left and the right? They got to be the same answer. Okay, so let's see what happens here. So this is one of these problems that there's a lot of math that's going to go on in your head. There's a lot of critical thinking you need to solve this, but there's literally not much to write down. So this is really good for you smart, lazy people that don't want to write stuff down, because this is all going to happen in your head. Okay, so let's think about what's going on here. So the top of our fraction, as x approaches 2 from the right, the top of our fraction just goes to 1, right? It's just a number. It's 1. What does the bottom of our fraction get close to? As x gets close to 2, it gets close to 0. Now, we never actually put 2 in, but it gets close to 0. But if I'm approaching from the right, I'm putting in what kind of numbers?
You're putting from the right.
So this is 2. I'm approaching from the right. So I'm putting numbers in like 3, 2.5, 2.1, 2.001, 2.00000000001. So this is getting 0, getting close to 0. But when I subtract, this is going to be positive, right? No, that plus 9 does not mean that's plus. That's a different plus. Okay. In this example, it's going to turn out that way, but I'll show you another example to show you that it's not always that way. Okay. So when I approach 2 from the left, I'm going to be putting in numbers less than 2. 1.9, 1.99, 1.9999, and so forth. So now, when I take 1.9 minus 2, I get a small 0 negative number. Now, if you take any number, 1, and you divide it by a really, really small number, what do you get? You get a really, really big number. So this is infinity.
That was a nice problem.
If you have a number divided by a really, 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 really small negative number, you get negative infinity. Now, bring up my calculator here. Should have had it up already. What does this mean in terms of this? So let's get my calculator going here. Maybe. So as I graph this, what was our limit from the right at 2? Infinity. What was the limit from the left? Negative infinity. So now consider the graph. What was the limit from the right? What is the limit from the left? We're now able to explain on a vertical asymptote where the graph goes to the left and the right of a vertical asymptote. If you remember last year when we did this, we just said, well, graph it and see where it's at, right? You knew there was an asymptote because the bottom was 0. Now we can say, well, as we approach in the limit, we know, does this go to infinity? Does this go to negative infinity? We can actually mathematically figure that out and don't have to just look at a graph. The graph verifies what happens, but we don't need that to be able to answer what happens. Okay. Now, does the limit exist? What's that? Did I lose you?
No. Not going through, but it's okay.
Okay, let's try, let's do this. We're going to switch it. Ready? So let's look at another one. So here's what I want to look at. Let's look at f of x is, and this will answer your question also, 1 minus x. Okay? And I want to look at the limit. Where is the vertical asymptote here? 1. So I want to look at the limit from the right and the limit from the left. So as I approach 1 from the right, if you need to like think of a picture, okay, I'm approaching from the right, so I'm putting in numbers bigger than 1. 2, right? 1.5. So if I take 1 minus 2, this is going to 0, but is it a positive or negative? If I'm subtracting numbers bigger than 2? Negative. The top doesn't change, so that's 1. So now I have a number over a really small negative, so this is going to negative. Here I am putting in numbers from the left. Numbers that are smaller than 1. So when I put those in, the bottom is going to 0 again, but it will be positive, which is telling me that's a positive infinity. If I go to graph this, before I put it in the calculator, we are going to have a vertical asymptote at 1. From the right, where is it going? Actually, that's wrong. That should not. That. And then from the left, it's going to infinity. There's my y-intercept. So I now know which way it's going. Does that make sense? That's what I was talking about.
From the left, it's positive.
Correct. Because when we come from the left, we're putting numbers in less than 1. And because it's 1 minus x, numbers less than 1, this is a positive. So this also goes back to your question. It's not always just plus plus. It kind of depends what the function is. Okay. All right. Let's try another one. Add some more x's in there. See how this affects stuff. So what is the limit as x approaches 3 from the right of 2x? Oh, negative. Nope. We're going to change this. This is a typo. Why do I have to make that negative 3? Why do I need to make this as x approaches? Because it's a plus 3. So if I put a 3 in there, I just get 6. And there's no 0. It's just 6 over 6. It's 1. So this is a typo. Oh, it's on your paper. It's just not up here. Okay, so I fixed it in your notes. So as we approach negative 3 from the right, so you're getting to negative 3. If I put negative 3 in the top, what do I get? Negative 6. If I put negative 3 from the right, so once again, if we think about negative 3, as I approach from the right, that would be a number like negative 2. So if I put negative 2 in there, is it positive or negative? Positive. So if I have negative 6 over a positive 0, what is that going to? Negative infinity, because I have a negative over a positive. If I put in negative 3 from the left, the top is still going to negative 6. The bottom's going to 0, but now I'm putting in numbers less than negative 3, like negative 4. If I put negative 4 in there, I get a negative. So now I have a negative over a negative. Which is positive. So you can see, this, we don't need this part necessarily to do this. So there's a lot of thought that goes into figuring that out, but there's not a whole lot of math we write down and calculations to do. You're just thinking through your head what's going on. Okay. So, as I've already kind of mentioned this, we kind of jumped to the graph part here already. This is how we can define a vertical asymptote. A line x equals a is a vertical asymptote of a graph if either from the right or the left goes to infinity. This is just definition of vertical asymptote. Why is it A instead of C? I don't know, just because they have for the line x equals A. Yeah, change it to a C if you want. You want to just make sure you change that to x equals C. Now, let me do one more example here before we move on. Imagine I had this. Imagine I had the limit of f of x as x approaches 3 from the right and from the left. I'm not going to say anything. You think about those. You got space on your paper in the right, bottom right corner or somewhere over there. See if you can write down what you think the answer to those are. So let's look at from the right. From the right, the top's going to 1. What happens to the bottom? It's going to 0. Is it a positive 0 or a negative 0 as you come from the right? It's positive. What about as you approach from the left? Why is it still positive? Because it's squared. So it goes to infinity. So, what about this? What about the limit at 3?
No. That's probably the answer.
It's the same.
Does it exist?
No.
Yes, because they're the same.
If the limit from the left and the limit from the right are the same, by theorem Bob, the limit here is also infinity. If you graph this, it looks like this. 1, 2, 3. Here's your vertical asymptote, and it looks like this. They're both going up. Okay. Now, back here, would we have a limit here of, if we just said, does the limit at 3 exist, at negative 3, excuse me, exist for these two? And we said, everybody's saying no, so there's no solution, it doesn't exist. Why does this not exist?
One's negative, one's positive.
Because, by what theorem?
Bob.
Theorem Bob. The theorem, Luke's going to go with theorem 3 all year instead of Bob. Theorem Bob, because the limit from the left is not equal to the limit for the right, therefore the limit at negative 3 does not exist. Okay. All right. So let's see here. whole bunch
I'm on the whole board?
of homework.
Well, no. I don't think we can. Well, just with COVID kicking up and stuff, we can't have.
Yeah,
It's
we're
gonna be the
passing
opposite.
around
They're
too
all
much
gonna be
germ.
quarantined at home all the time.
No.
You'll talk to vaccinated together, yeah.
For that one,